Okay, let's continue the lecture. So we talk about the crystal structure, and then the uh, to to indicate the direction of crystal structure, we're going to use the Miller indices. For direction, we use the Miller indices we use to identify direction and plane in the crystal materials. So for direction, the we use the vector like this is a direction. This is like a directional vector, and then you use this particular bracket for the direction that I explained you in the previous slide. For plane, right? Then you can use the set of integer with this particular bracket. So to define a plane, right? Basically, for example, to define a plane, like this red plane, you should think about the vector is orthogonal to this plane, right? So for this particular plane, the vector will be like a 1, 1, 0 direction because it has uh, in that the vector orthogonal to this plane, there is no g coordinate change, but there is x and y is proportionally changed. So that's 1, 1, 0 the direction, right? Um, so so think about the vector orthogonal to the particular plane. So well, basically in Miller indices, you should think about this step. Take the intercept of the plane with the three axes, and then take the reciprocals, and then multiplying the smallest common denominator to make integer. That's kind of step that you're gonna you can take a look into to put some Miller indices. Okay. Let's talk about silicon atomic structure. Silicon has a diamond cubic structure. As you see in this figure, we have atoms around the 8 corners, and then you have half atoms at each six surface, and then inside of the volume you have like four atoms in it, and then they are connected by covalent bonding, and then their lattice parameter. So this structure is repeated. That's the lattice parameter over here. A is 5.43 angstrom, and then their percent of volume occupied by atom is APF. As I said, the atomic packing factor is 34%. Comparing FCC, 34% is less than the FCC. And then, well, regarding the relationship between the lattice diameter and then and radius of the atom, they in this relationship. Okay, and well, when you make like a silicon wafer, basically you have three different directionality of the wafer is available. It's a 100 in the left, and then 110 plane is like this, okay, and then 111 plane like this. So this particular plane is located on top of the wafer, okay. So depending on uh, your fabrication purpose, normally you use the 100 plane, but depending on your fabrication purpose, you can purchase 110 plane silicon wafer or 111 plane of the wafer. Okay. Okay. For silicon properties, right? Silicon properties is silicon is the semiconductor, and then it also is good mechanical material as well. So their density is like this, and then their band gap. Their intrinsic their band gap is 1.12 electron volt, and then their intrinsic resistivity is 2.3 times 10 to the 5 ohms centimeter. Okay, so it's not it's high. Uh, So more, so intrinsic, more, so people you dope the semiconductor, is not conductive, right? And then if you put the doping and then their resistivity changes, like in between the 1 to 10 ohm centimeter, is comparing their intrinsic resistivity. This is smaller, so now it becomes conductive. So that's the beauty of the doping, like N-type or P-type doping, and then you can make certain portion of the layer to be conductive. Okay, so that's the beauty of silicon. The Young's modulus is depending on the directionality, because its crystal structure has directionality. So 100 direction, it has 131 gigapascal, and 111 direction is 187 gigapascal. So it's an anisotropic properties. The Poisson ratio is 0.29, and then the maximum stress means their kind of ultimate strengths that withstand the maximum, the withstandable stress is 3 times 10 to 10 Pascal. That's the let's see 30 gigapascal. 30 gigapascal is the maximum stress the silicon structure can withstand. And then silicon is brittle material, right? Coefficient of thermal expansion is 2.6 times 10 to the minus 6. That's the, I mean, it's low comparing other metals. Melting point is 1421 degrees C, and then it has piezoelectric resistive as well, and then dielectric constant like 11.8, refraction index 3.42. So that's why compare, if you take a look into the property of silicon, it's very attractive material for some MEMS structure, like some cantilever structure with out of silicon, because it has a good Young's modulus, and then the good maximum stress, even though it's brittle. So it's not brittle. It's not really good property, but it somehow it provides a stable structure for some MEMS structure. Okay. Wafer specification. This is talk about the silicon wafer. So growth method is a really fascinating way that you can build the silicon wafer. So the guy who find out the way to grow the silicon wafer is Kjol Kolarski. Is I think it's a Russian guy. If you Google it, then his way to grow the silicon is really amazing. It starts with oriented seed of silicon, and then you can grow from the seed. Like you just grow your crystal structure from the seed of crystal of seed. So please take a look into the some YouTube to the way to grow the wafers. Actually, I'm going to link some of the YouTube link that to cover all the fabrication process. In the process, you're going to see this Kojarski method. So depending on the orientation of a crystal structure, you can grow like a 100 direction or 110 or 111 direction. So you can choose either of the three orientation when you buy silicon wafer. And then their diameter also available from the 2-inch to the up to the 12-inch. And then for dopant, you can use the boron or phosphorus for P-type and then N-type respectively. Primary flat is in 011 direction. You have a primary flat, and then depending on the orientation, you have secondary flat. That I already talked about this. Thickness usually half millimeter. for 4 inch, and then there are some thin and thicker wafer maybe available at the other side. Bow means the how much it was kind of a bowed over the wafer, so that should be less than 40 micron, and taper also the less than 25 micron. Flatness should be, I mean, if you really good quality is devices, make sure you buy the polished one. Is that they guarantee the less than 100 nanometer flatness, roughness. Resistivity, you can buy the conduct 3 to 10 ohm centimeter one that you can choose. So basically, you can have like a conductive one or semi-conductive one. You can buy it. Polish it. You can either polish it both sides or polish it only one side. So if you need the backside etching, then you should buy polished one for the double side. For the grade, you have if you have one like grade, test grade is cheaper than the prime, so you can kind of build your kind of fabrication procedure on test grade, and then eventually you can move to the prime grade to build your own build the devices. Okay. All right. There are some terminology in etching. So etch rate is the rate of removal of material. So that should be some length over a time. So it could be angstrom per second or micrometer per minute. Uniformity is the this is the measurement about uniformity of etching through the whole vapor. So you can find out the etch rate at highest etch rate in some portion of the some part of the vapor, and then you can find out low etch rate, and then it is the difference over the summation. That's called uniformity. If they are uniform, if high and then low etch rate is no difference, then it becomes zero, right? So zero means it's really uniform on whole, on whole vapor. And isotropy means the etch rate as a function of direction. So like a silicon, the etch rate is different because of the crystal structure. Lateral etch rate ratio is the ratio between the horizontal etch rate over vertical etch rate, right? For isotropic etch, it could be equal to 1, right? Depending on etching, what etching material and then the direction of the silicon vapor. For example, at 85 degrees C, 58% of KO etching, depending on the directionality of the silicon vapor, like a 110 versus 100 versus 111, you can see their etching rate is different, like a 400 and then 200 and 100 for that particular direction. So that means in 110 direction, it is 400 times higher comparing to the 111 direction. So that's why you have like a pyramid shape of the etching is possible, because 110 and 100 direction is much the etching rate is much higher than the 111 direction. Okay. Over etching means it's produce the undercut profile. That means you etch more than you necessary to do. And selectivity is the basically the ratio between the etch rate of your target film and versus your etch rate of a mask, right? For example, if you wanna etch the silicon vapor, some portion of silicon vapor, while you're using the photoresist as a mask, then the ratio between the two is their selectivity. You want to have high selectivity for your target film, right? That means your mask material can protect well during those etching process. Okay. Loading effects, effect of total area to be etched, like because of the physical size of wafer, um, even though you put the whole wafer into the some wet chemicals, probably some area in the middle is they are etched faster than around the edges. So that will be affected by the how much opening area is available. If you have lots of area to be etched, then there are some effect by this opening area, right? So that's kind of the things that we call this a loading effect. Feature size effect, and then aspect ratio also effect on the etching capability or etching characteristics. Okay, physical and chemical etching. So physical etching, you need some physical way to etch the material. Chemical etching means you use some chemistry to be etched. Okay, so chemical etching is based on chemical reaction like HNA etching and KOH etching on silicon. Liquid phase or gas phase etchant is usually used, and then you can be isotropic or anisotropic. Also, it has high selectivity comparing your mask material and your target material is usually high selectivity. For physical etching, actually you based on the physical collision of your ion or electron to the target material. So ion beam milling, you use the momentum of energetic beam of atoms. That's you use momentum. So because it has certain directivity of the ion, so it has high anisotropic result. Okay, and then also it has low selectivity because the nature of the way is physical, not the chemical. So if you want to have like a really good vertical like a wall during the etching, then physical etching is recommended. But make sure you have a very good mask because they are low selectivity. If you want to have like an anisotropic etching, then you should go to the chemical etching, and then the selectivity is high. Sometimes the physical and chemical etching was used together, like RI is a reactive ion etching, so they are using both way. It's kind of synergetic effect. Range of material that possible by the physical or chemical etching is silicon dioxide, silicon nitride. Most of the metal is possible to use, some organic material, some polymer photoresist, or so most of the material then used in clean room, solid material, I mean, that's possible to be etched either by the chemical or physical way to etch. Okay, let's compare the wet and then dry etching. So wet etching means you use chemicals, and dry etching is you use certain ions and electrons in dry condition. Okay, so in wet etching, if you want some isotropic properties, and then this is recommended wet etching chemicals, HNA for silicon and BOE for silicon dioxide. If you want to have an isotropic etching, and KOH, TMAH is good for silicon. Okay, so that's KOH or TMAH is popular for like a backside etching, to have an isotropic etching to make an opening to the other side of the hole. Dry etching, you can you can use the either plasma-based method or without plasma. Okay, with the plasma-based one, well, we can use the physical or physical plus chemical. For physical, you can use ion beam milling. Physical plus chemical, you have RI or ICPs available. ICP is popular to make a very deep etching. Um, so you can achieve very high aspect ratio of structure through the ICP. Without plasma, you can use uh, XEF2 for silicon. So those are methods available to choose. Okay. So etching process, for example, an isotropic etching, you see the let's see, an isotropic etching, you have same etch ratio either vertical or lateral because it's isotropic etching. For example, you see, so what? Let's say you have like a undercut with by the over etching, then you can expect like a radius over here. This is like the lateral and then vertical etch rate is same. So undercut shape is like this radius. Okay. Um, if you keep doing this etching, because they are isotropic, uh, isotropic nature, it just keep going down. Then you can make going further, like intentional over etching. Then you can move, you can go like this. So some people using this method to make like a sharp tip on the surface of the structures. Like let's say this is like a um, negative photoresist like SU8, and then you keep etching using an isotropic etching method, then eventually you can have a very sharp tip if you do over etching, right? Okay, if you wanna an isotropic etching, you can use the KOH, right, or RI. Right, wet etching. This is kind of a mechanism how wet etching is going to work. Okay. Um, So, so first step is a reactant transport to the surface to the target, and then reaction happen here through the target. This is like a gray is the target material, and then this orange is the protected mask, protection mask, and then after the reaction takes place, and then product transport from the surface. Okay, so I mean this is just a natural process. Okay, if step 103 is rate determining, etching is diffuse unlimited, so maybe increased by steering. So when you do wet etching, so in that case you kind of shake your device during those wetching etching, because the shaking actually you guaranteed like a uniform etching rate whole over whole vapor. Okay, and concentration and diffusion coefficient is important. If number two is H rate determining, then etching is reaction rate limited, right? If this number two reaction is determine your etch rate, and then this is strongly depends on temperature and material and solution composition. Right. Okay. So there is a this is definition of a diffusion coefficient and reaction rate based. Okay. So there are some equations available, um, but I'm not going to cover in details on this. So these are the like a um, function of like a temperature and then the Boltzmann constant here. Okay. Isotropic etching of silicon is you can use PNA. PNA is like this is like a reaction step, that oxidation by charge transfer and then dissolution reaction and so on. Uh, I'm not really familiar with this detailed step of the etching process. So basically, this is the kind of a series of chemical reaction happen over there. Uh, Well, concentration also determine the HS rate. Uh, let's see, if you have high, in HNA, you have hydraulic hydrochloride. So we have a mixture of HF and then you have HNO3 here. HNO3 is a nitric acid. Uh, so depending on this, their composition, like a high HF and then low HNO3, and then the H rate is controlled by HNO3 concentration, and then the oxidation step. And then if you have a composition at the other side, then H rate controlled by the HF concentration, and then okay. Agitation is important in this step, and then the good masking material for HNA etching is silicon dioxide. Okay, so they etching by the per minute they etch it by 300 to 800 angstrom. It's good for shallow etching, but if you want a really deep etching, you need a good protection. In that case, gold or silicon nitride is good, right? So it depending on, or just because this number is given, you can imagine that how much time you need to etch a certain material. Okay, so you should have choice whether you want to have a really good protection or like a shallow protection during this etching. Isotropic etching of silicon dioxide, silicon nitride, or you can use the diluted HF, and then there is a chemical reaction here, or silicon nitride, and then it's also etched by HF, but much slower than silicon dioxide. Okay, so in that case, H3PO4 is recommended for silicon nitride. The selectivity usually 10 to 1 for nitride of oxide and 30 to 1 to nitride of silicon. So polysilicon is good masking material for silicon nitride etching using this H3PO4. Okay. All right. Let me stop here and then continue at the next slide.